There are several different types of sources which inject different source profiles. The planewave source simulates a wave with parallel wavefronts where the phase is uniform across each wavefront. This is the same type of source that we saw used in the My First Simulation section at the beginning of this course. Planewaves can be injected at a specified angle, and this movie shows a planewave source pulse traveling in free space at an angle. The movie is showing the real part of the Z component of the electric fields, so we can clearly see the angled wavefronts. The plot on the right of the movie shows the field profile from a frequency domain monitor, which gives the steady-state response at a specific frequency. There are 3 different plane wave source types that you can select from in the source settings: Bloch periodic, BFAST, and Diffracting. You can select the type of plane wave to use depending on the use case. We typically use the plane wave source to represent beams that are incident on periodic structures where the spot size of the beam is much larger than the period of the device, so the beam width can be approximated as being infinitely large. We can then simulate just one period of the structure with periodic or Bloch boundaries at the sides and use the plane wave source. Use cases are shown here, where a single unit cell of the periodic structure is included in the simulation region, and PML absorbing boundaries are used above and below the structure to absorb any reflected or transmitted light. In case 1, light is injected at normal incidence. In this case, the Bloch periodic plane wave type is used in conjunction with periodic boundaries at the sides of the simulation region. In case 2, light is injected at an angle away from normal. If the source is single frequency, then the Bloch periodic plane wave should be used in conjunction with Bloch boundaries at the sides. For the broadband case, the BFAST type source is recommended. When using the BFAST source, BFAST boundary conditions will automatically be used at the sides of the source. Let's go into why we use different source and boundary conditions for angled injection. The Bloch boundary conditions are similar to periodic boundaries, but they take into account the phase difference between each period of the device for the given injection angle of the source. The Bloch boundaries enforce a constant phase difference between each unit cell regardless of the wavelength, so if you were to inject light over a broadband range, the angle of injection will vary as a function of wavelength in order to fulfill the phase constraint of the Bloch boundary. Here's an example where, although the angle theta setting is set to 30 degrees, only the center frequency is injected at 30 degrees, and the angle varies over the frequency range. Because of this, the Bloch boundaries are only recommended when running single frequency simulations. For broadband simulations, the BFAST source type and boundaries should be used. BFAST is short for Broadband Fixed Angle Source Technique, and it allows the injection of light at a constant angle over the broadband wavelength range. When using the BFAST plane wave source type, the sides of the simulation region will automatically use BFAST boundary conditions. Note that BFAST can be used for single frequency simulations, but it's not typically recommended since it requires more computational time compared to using the Bloch periodic plane wave with Bloch boundaries. For more information about how BFAST works and tips for using BFAST, go to the knowledge base. The relevant links are listed below. In addition to using plane waves to represent infinitely wide sources, it's also possible to simulate a plane wave diffracting through a rectangular aperture of a given size. You can do this by using the diffracting plane wave source type, where the spans of the source determine the size of the aperture. For example, in the well-known Young's double slit experiment, a plane wave diffracts through 2 apertures, and the image of the interference pattern between the light from the 2 apertures is projected onto a screen some distance away. We have an example of the double slit experiment simulated using plane wave sources in our online knowledge base. As you see in the image on the left, we use 2 diffracting plane wave sources to represent the light passing through the 2 apertures. You'll find a link to this example below this video if you want to try out the simulation file. When using the diffracting plane wave source type, the sources should be contained within the simulation region and shouldn't intersect with the boundary conditions. The boundary conditions can be set to PML if you want to simulate open absorbing boundaries. The source spans determine the size of the aperture that you want to represent. Now that we've gone over the three types of plane wave sources, Bloch periodic, BFAST, and diffracting, let's go over some common pitfalls and ways to correct them. The first one is trying to represent a diffracting plane wave by using the Bloch periodic plane wave type and setting the span of the plane wave to represent the aperture size. The reason this can't be done is because the source injection plane will automatically be extended to the full width of the simulation region, so you can't specify a smaller span. You'll need to use the diffracting plane wave type to set a specific span. The next example is using the Bloch periodic plane wave type to simulate a broadband source traveling at an angle. As we saw previously, when you do this, the light propagation angle will vary with frequency. Instead, you can use the BFAST plane wave to inject light at a constant angle over all wavelengths. Another situation is using the Bloch periodic plane wave for non-periodic devices. When non-periodic boundaries such as PML or metal boundaries are used, this will truncate the source at the sides of the simulation region and lead to edge effects as illustrated in the figure here. Instead, you should use a finite-sized source such as a Gaussian beam or total field scattered field source, and both of these sources will be discussed later on in this section. Finally, you can't use the BFAST plane wave to simulate non-periodic devices, and the reason for this is because the BFAST boundaries assume a periodic structure, so the results that you get from the simulation would be as though the source is infinitely wide and the structure is periodic, with the period being equal to the span of the simulation region. Again, you can use a finite-sized source like the Gaussian beam or total field scattered field source instead. You can use the flowchart on this slide to choose the plane wave source type and boundary conditions to use depending on the use case. A copy of the flowchart can also be found below for you to download and refer to. Some common applications which use the plane wave sources are solar cells, CMOS image sensors, metamaterials, and diffraction gratings. For the solar cell and CMOS image sensor design, we commonly vary the incident angle of the source and obtain the optical absorption collection efficiency of the design as a function of source angle. In the next unit, we'll go through a demonstration of a diffraction grating where we'll set up a plane wave source and measure the fraction of power which gets reflected from the grating.